Good day, everyone. This is the course for KIG1015 Dynamics. For the starts, let's have a look on the introductions of dynamics. This is the outline of today's lectures. We'll start with what is mechanics, the introductions of dynamics itself, then is followed by the fundamental concept of dynamics, the principles of dynamics, system of units used in dynamics, methods of problem solutions, how we solve a problem that involve dynamics, and the numerical accuracies, how to ensure the solution that we obtain is accurate enough. What is mechanics? Mechanics is the studies of bodies under the actions of forces. Here we describe or predict the conditions of the bodies at rest or in motions under the actions of forces. The bodies here could be represented by particles or rigid bodies. In year 1, static subjects, we study the conditions of the bodies at rest or at a constant velocities. So now in year 2, dynamics, we study the conditions of accelerating bodies. Here is referring to particles or rigid bodies. So a lot of time these two subjects is combined and is called applied mechanics. Is an very important subject in mechanical engineering. Besides applied mechanics, we also learn the conditions of deformable bodies, as we have learned in year 1 subjects, mechanics of materials, sometimes is called a strength of materials. Other than that, we also studies the conditions of fluids, here referring to gas or liquids in fluids mechanics. Mechanics is an applied science closely related to physics, so many of the concepts will build on that prior knowledge. We can say that mechanics is the foundation of many engineering topics and is an indispensable prerequisite to their studies. For example, you learn static first before you learn mechanics of materials, and now you learn dynamics. Let's have a look on the overview of statics and mechanical materials. In statics, we assume that the bodies that we are analyzing is rigid. It cannot be deformed. So, however, in real scenarios, materials will deform and it is only able to sustain a certain loads. So what we have learned in mechanics of materials, we assume the body that we are analyzing is elastic and can deform. In statics, we use equilibrium conditions to solve those unknown reaction force and moments to evaluate the conditions of the rigid bodies. Whereas in mechanics of materials, besides the equilibrium conditions, we learn the deformations that lead to compatibility conditions. We have additional equation to solve those unknown reaction force, which includes the statically indeterminate case. To recap back, so statically indeterminate case are those that where the numbers of the unknowns to be solved are more than the number of equations obtained from the equilibrium conditions. So here in mechanical material, with the additional equation from the deformations that we have learned, we can use it to solve those statically indeterminate case. In statics, we learn vectors. We solve the reaction force of a structure under loading using the equilibrium conditions. And we also find the internal forces in members such as shear force and bending moments. In mechanics of materials, we extended what we have learned in statics, the vectors, the reaction forces, the internal forces that we have calculated. We use it to find the stresses and the strains, including their transformations. We also use the material properties and relate it to material strengths. In mechanics of materials, we find also the deflections of the structures, particularly the beams, subjected to a load. And with what we have learned in mechanics of material, we can come up with a proper design of the structures by considering the factor of safety, the stress, the strains, the deformations subjected to external loads. Let's take this bridge as an example. What can you do with the statics of mechanical material knowledge that we have learned? First, we calculate the forces in each member of these structures, the truss system in this case. Then we use what we have learned in mechanics materials to design a proper, stronger structures of this bridge so that it can withstand the load that it will experience. In the fundamental concepts of dynamics, we deal with space, time, mass, and force. Space is defined as the position of physical bodies and their extents. The positions of any object is defined relative to a reference point, usually is called the origins. These positions of the objects is specified by either linear or angular distances of the object from the origins. Next, time is a measuring system used to compare the durations of events and the intervals between them. Usually we use it to quantify the rate of change, such as the motions of objects. Next, mass. Every physical body has some inertias. It offers resistance to the change in their course of motions. As per the concept of mass, each body has certain amount of mass which cause the inertia and gravitational attractions. Finally, the force is about the interactions between the physical bodies in terms of the force acting between them. This interaction can be through contacts like books placed on the tables or without the contacts like a gravitational pulls. The force is defined by its magnitude, directions, and the point of applications. Force acting on the bodies tend to move it in the directions of force. In Newtonian mechanics, where we apply Newton's law, space, time, and mass are absolute concepts, independent of each other, whereas force is not independent of the other three. The force acting on the body is related to the mass of the bodies and the variation of its velocity with times. In dynamics, we deal with two types of bodies. First, the particles is a very small amount of matter which may be assumed to occupy a single point in space, whereas rigid bodies is a combination of large number of particles occupying a fixed position with respect to each other. In particles, there is no rotations involved. In rigid bodies, we assume there is a rotations involved. We will be dealing with several principles in dynamics. First, Newton's first law, summation of F equal to 0. Here, particles remain at rest or continue to move with constant velocity when there is no unbalanced force acting on it. Next, in Newton's second law, where we have this summation of F equal to ma, we are dealing with accelerating bodies. The accelerations of a particle is proportional to the vectors, sum of the forces acting on it, and is in the direction of these vector sums. In Newton's third laws, it stated that the forces of actions and reaction between the interacting bodies are equal in magnitude but opposite in directions. Beside of these three Newton laws, we have also Newton's law of gravitation. The two particles are attracted with equal and opposite forces. We have these parallelogram laws, the concept of the resultant force, principle of transmissibility, a concept of the same line of actions. For the systems of units in dynamics, We are dealing with several units, particularly called kinetics units. Here is referring to length, that is dealing with position, the times, the mass that is dealing with the inertias, and force. As mentioned earlier, the position, times, and mass are independent to each others. They are referred to the three basic kinetic units. The fourth unit, which is referred to derived units, is a force. As mentioned, is a dependence to the position, time, and mass. It has a definition compatible with Newton's second laws, F equal to ma. In SI units, the basic units are length, time, and mass, which are arbitrarily defined as the meters, seconds, and kilogram, kg. Whereas force is derived units, which is equal to Newton, equals to kg ms power of -2. In US customary units, the basic units are length, time, and force, which are arbitrarily defined as the foots, seconds, and pounds, whereas here mass is a derived units, pound second square per feet. In solving problems involving dynamics, first we have to understand the problem statements. We need to include given data, specification of what is to be determined, and figure out what are the quantities involved. Next is the free body diagrams, FBD. We create a diagram of the bodies which involve all the forces acting on each bodies. We have learned extensively in statics and mechanics of materials. We will then next to decide the fundamental principle to be applied to express or to determine the conditions of a body, whether it's at rest or in motions. The rules of algebra are usually applied to solve the equations for the unknown quantities. Finally, we need to check our solutions. We need to test for errors in reasoning by verifying that the units that we are using to compute the results are correct. We also can test for error in computations by substituting the data that we have and the computed results into others unused equations on the other 6 principles. We need to be always apply experience and physical intuitions to assess whether the result seems reasonable or not. For example, it is not reasonable to have a times taken of hours for particles to travel from point A to point B of a 6-meter distance. Finally, the numerical accuracies. The accuracy of a solution depends on two things: the accuracies of the given data and the accuracies of the computations performed. The use of hand calculators and computers generally makes the accuracies of the computation much greater than the accuracies of the data. The solution accuracy is usually limited by the data accuracies. So remember what you learned about significance figures. If we compare statics and dynamics, here we see that statics is the analysis of body at rest, whereas dynamics is the analysis of body in motions. Here we deal with kinematics and kinetics. Kinematics is studies of geometry of motions where we relate displacement, velocity, accelerations, and time without considering the force acting on it. Whereas in kinetics, we consider the force and we study the motions caused by these forces. In statics, we use equations of equilibrium to study the conditions of particles, summation F equal to 0, and the rigid bodies, where the rotation is involved, summation M equal to 0. Whereas in dynamics, we use equation of motions. In the right-hand side, we have the accelerating motions, MA. So it studies particles as well as rigid bodies when we have the accelerations involved.